Hey everyone, welcome. Today we are jumping into something really special in the Go programming language. We're talking about interfaces. And trust me, this is a feature that's going to totally change the way you think about putting your code together. And just to get our heads in the right space, I want to throw this out there. What if an integer and a function could do the exact same job? I know, it sounds kind of weird, doesn't it? But stick with me, because by the end of this, you're going to see exactly how Go pulls this off. All right, so this whole thing, this entire concept, it all boils down to one really powerful idea. In Go, we don't really care so much about what something is. What we really care about is what it does. And that's what we mean when we talk about a contract for behavior. So what is an interface, really? Well, in Go, it's a type, yeah? But it's a special kind of type. It doesn't actually hold any data. Think of it more like a blueprint. It's just a list of method signatures. It's a formal way of saying, hey, whatever you are, I don't care, I just need you to be able to do these specific things. And this one sentence, this, right here, captures the entire philosophy behind Go's amazing flexibility. If something can do this, then it can be used here. Just think about that for a second. It doesn't matter if you're dealing with a file on your computer, a connection over the internet, or just some data in memory. If it fulfills the contract, if it knows how to write, then you can plug it in anywhere a writer is expected. It's really that simple and that powerful. And you see this idea everywhere in Go's standard library. Go absolutely loves small, super focused interfaces, a lot of them with just one single method. This is why you run into types like io.writer, io.reader, or the stringer interface all the time. They do one thing, they do it really well, and that makes them incredibly easy to reuse all over the place. Okay, so how does this whole philosophy of doing versus being actually play out in real code? Let's get practical. We're going to create a simple data type and check out two completely different ways to give it the behaviors we want. All right, here we go. Here's our custom type, sequence. Super simple, it's just a slice of integers. Now our goal is to give this thing two new superpowers. We want to be able to sort it, and we want to be able to print it out in a nice, clean way as a string. So we've got a couple of ways to tackle this. On one side, we could go the traditional route and make our sequence type implement every single method that the sorting interface needs and all the methods the printing interface needs. But Go gives us another way, and it's often a lot cleaner. It's called type conversion. So instead of permanently bolting on all this functionality to our type, we can just temporarily convert our sequence into, say, a sort.inSlice, just for a moment, only to use its sort method. We're essentially borrowing that behavior just when we need it. And this, right here, this isn't some weird hack. It's a core pattern in idiomatic Go. This idea of temporarily changing a values type just to get at a different set of methods, that's how you keep your own types small and clean while still getting to use all the awesome functionality built into the standard library. Okay, so we get it. Interfaces are all about behavior, but they also kind of act like containers, right? A variable that has an interface type can hold a value of any concrete type that satisfies that interface. And that leads to a whole new question. How do we figure out what's actually hiding inside? So picture this. You get a value, and its type is interface. Now that's the empty interface, which means it can hold literally anything. It could be a number, a string, some custom struct you've never seen before, anything. How in the world do you safely find out what it is so you can actually work with it? Well, the answer is something called a type assertion. This is Go's tool for basically saying, you know what? I have a strong hunch that the value inside this interface is actually a string, or I'm pretty sure it's an integer. It's you, the programmer, making an explicit request to unwrap the interface and get that concrete value out. But, and this is a huge but, there's a catch. If you're wrong, if you assert that the value is a string, but it's really an integer, your program is going to panic. It's going to crash hard. This direct assertion is basically you telling the compiler, look, I am 100% positive about this type, and if I'm wrong, well, I accept the fiery consequences. Yeah, so thankfully, to avoid all that crashing and burning, Go gives us a much, much safer way to do this, the comma OK idiom. This version of the type assertion gives you back two things. The first is the value you wanted, but the second, and this is the important part, is a Boolean,
We usually call it OK. That just tells you if your guess was right. If OK is false, it means the type wasn't what you thought, but hey, no crash. Your program keeps running. You can just handle it. This is absolutely the safe, standard way to check what's inside an interface.
Okay, let's step back for a second. We've got the mechanics down. Now let's zoom out and see how this all builds up into a really powerful design philosophy. We're talking about building entire systems where different pieces can just plug together, like Lego bricks. So here's a really powerful design pattern you see in a lot of great Go code. You only export the interface from your package, and you keep the concrete implementation, the actual struct, private. And what this does is it sends a crystal clear message to anyone using your code. It says, hey, you should only care about the behavior I'm promising you in this interface. The nitty-gritty details of how I make it happen, that's my business. This forces you to write decoupled code and makes your systems way more flexible down the road. And you don't have to look far to see a perfect example of this. Just check out Go's crypto libraries. They define these really simple interfaces like block, which just knows how to encrypt a single chunk of data, and stream, which describes a stream cipher. All the complex details of AES or DES or whatever algorithm is being used are hidden away behind these simple, clean contracts.
And this is where it all pays off. Look at this function signature here. It takes a block as an argument, but it has absolutely no idea what specific algorithm is hiding inside that block. It could be AES, it could be something someone invents tomorrow. It does not care. As long as that object you pass in satisfies the block contract, it just works. You know what that means? It means you can swap out the entire encryption algorithm for your whole system with a one-line change. That's insane.
All right, time for the grand finale. Let's pull all of these ideas together, behavior, conversion, abstraction, and see them in action in what is probably the most famous, most powerful example of Go's interfaces, the HTTP package. Right at the very heart of Go's web server is this one single interface, http.handler. It has just one method, serve HTTP. And the rule is incredibly simple. If your type has this method, it can be a web server. That's it. That is the entire contract. So what does that actually mean? Well, a struct can be a web handler. Okay, sure, that makes sense. You can store state in it. But because of interfaces, an integer can also be a web handler. A channel can be a web handler. And, maybe the most mind-bending of all, a plain old function can be turned into a web handler. Just think about that. 4 completely different kinds of things, all doing the exact same job, all because they satisfy that one simple, elegant contract. And this is the secret sauce. This is why it all works. At the end of the day, interfaces are just sets of methods. And since Go lets you define methods on almost any type you create, it means almost anything can be made to satisfy an interface. That simple combination is what creates all this incredible power, letting you build systems that are just so elegant and so flexible. So, I'll leave you with this to think about the next time you're starting a new project or designing a system. What if you stopped thinking so much about what your objects are? What happens if you focus only on what they do? What new doors open up when you start prioritizing behavior over implementation? Thanks so much for tuning in.